Today we will discuss a few problems from subspace and which are left for you in your note 3 shared to you, and then we will recall few basic things from quotient space, or means quotient topology, and one or two problems from quotient space. Okay, and actually at the beginning the problems are taken from your note 3, means we shared to you based on the subspace topology, and there's a few problems. We will first solve those problems. Okay, so first one is, can you see my screen?
Yes, sir.
Yes. Okay. So now read the question first. That suppose we have topological space X. Suppose tau is the topology there, and Z be a Y be a subspace, and Z means Z and Y are subsets, and both are non-empty sets, and where Z is contained in Y and Y is contained in X. Then we claim that means then the topology, the subspace topology on Z induced from X is same as the subspace topology on Z induced from the subspace topology on Y induced from X. Means, so can you say what is it? Means this tau Z means what are the open sets? U intersection Z, right? Where U belongs to
X.
No, it belongs to an element.
Tau.
Yes, U belongs to tau. And what is tau Y and then Z? This is
U intersection Z, U belongs to tau Y.
Intersection Z such that U belongs to tau Y, right? Yes. So now, can you quickly prove this one? Say, suppose tau of Y of Z contained in tau Z. So, how do you prove?
Take an element from
Yes,
tau
take an element
YZ.
from tau YZ. Say it is W tau YZ. Then this implies W will be the form. W will be some V intersection Z, right? Where V belongs to tau Y. And again, since V belongs to tau Y, V belongs to tau Y implies V is equal to U intersection Y, and therefore W is equal to U intersection Y intersection Z. But what is this Y intersection Z? This is Z, and therefore yes, therefore W belongs to tau Z. Sorry, this is W belongs to tau Z, right? Okay, fine. This way is done. Now tell me the reverse one. Tau Z contained in tau Y Z. So how do you start again? So take an element W from tau Z, then
There exists U belonging to tau.
yes, U belongs to tau such that
U intersection
U intersection Z equal to W, right? Right? Now W is equal to U intersection Z. Z means Z intersection Y, right? These are set theory. This is U intersection Y intersection Z. Now this one belongs to tau Y, right? And therefore W belongs to tau YZ.
Tau YZ.
Yes, exactly. And so we have the equality. So tau of z is equal to tau y z. Okay. Let's come to the next problem. So here we have a topology tau on X, and we took a subset Y. Of course, it's non-empty because with M2 we have nothing with M2, like we have nothing to deal with. Okay, so we take a non-empty subset Y, then as usual we can define a subspace topology on Y and say it is tau Y. Okay, then if beta, the script B, is a base for X, means is a base for X comma tau, then if we consider this collection, this will be a base for Y comma tau Y. Okay, so is it clear? Now tell me, so what do you mean by, so if you are given a topological space X tau, so what do you mean by a base? So we say beta, say script B is a base for tau, or base or basis. So it means, what does it mean?
For every open set in tau can be written as a union of elements in beta.
Yes, every open set in tau can be written as union of elements of beta. Is it the only criteria?
No, sir. Other definitions also.
Yes,
Means beta covers X first property.
Yes, beta covers X, right?
X.
So actually,
that is for all X belongs to X, there is an element in beta.
Yes. Actually, always try to say the second one. Okay, we say a collection beta. It's of course a subcollection of tau is a base if for any X belongs to X, any open set U, and for X belongs to U, there exists some B belongs to script B such that X belongs to B subset of U, right? Now you have to verify this statement in this collection for the topology tau Y. So how do you verify? Yes, one case is easy, right? So what you said, that you can take Y as union of U intersection Y, where U belongs to this script B. This one is obvious, right? There is nothing to prove. Now give the second one. Take an element. Okay, so how do you proceed for second condition? Take X belongs to
B1 intersection B2.
Yes, B1 intersection B2.
Then there is just a B3.
Yes. So B1 intersection B2 means you have to take U1 intersection U1 intersection Y, right? So what are the elements of this beta Y? This is U intersection Y. So you have to take elements of this form, U intersection Y and U2 intersection Y. Now take an element from the intersection. Okay, there you have to find out another set of the form, say some U3 intersection Y, which lies in the intersection. Okay, so now X belongs to here. So what does it mean? This means X belongs to U1 intersection U2 intersection Y. And now we will use the base property of the script B. So this is this belongs to C. U1 and U2 belongs to script B, and X is an element in the intersection, so there exists by definition there exists some u3 belongs to script B such that x belongs to u3 subset of u1 intersection u2. Just take the intersection by y in both sides. So x belongs to u3 intersection y subset of u1 intersection y intersection u2 intersection. Okay, so this is the complete answer. Whenever the question asked means the question asks all the elements of this form. Okay, so all the elements of this form, and they you have to deal with this kind of sets only. So you cannot start with just simply taking B1 and B2 from beta. Okay. Of course, you can, but this B1 and B2 will B1 will be of this kind of forms, and B2 will be of this forms. Okay. Third problem. So, can you quickly solve this one? Just take 5 minutes and or 2 minutes and tell me how to proceed. It's easy. It's just a definition of closure point. Okay. Here B is a subset of Y. Okay. Yes. So what does this mean? Say X belongs to C, L, Y, B. What does it mean? For
every open set
any open set
containing X in B tau
in
B tau
B tau.
Means topology on B.
Why topology on B?
Since you have learned closure.
We are taking topology over. That's why here Y is written, right? We are taking topology over Y.
Yes, sir.
Yes. So you have to take any open set containing X in the topology Y comma tau Y only. Yes. Okay. See here B is simply a subset, but and two topologies are here. One is X comma tau. This is our parent topology, and we are taking a subspace topology Y comma tau Y. Okay, and here that this closure of B is with respect to this topology. That's why Y is written, and here this closure of X with respect to this topology X comma tau. And after taking this closure, we are taking this intersection. Okay. Now for any open set, yes, then
its intersection B will be non-empty.
Say open set U or say open set V, then V intersection B is non-empty, right?
Yes.
Yes. Now V is open means V belongs to tau Y, right? Then V is equal to
V can be written in the form of open set of U in topology X intersection Y, where U is open in X.
U belongs to tau, right? Just say U belongs to tau. You don't have to tell always that U is open in X. Just say U belongs to tau. That's it. This means U is open in X. Now this V equal to intersection tau Y. Now this can be written as, so therefore from here U intersection, we have to start with other one. So we have taken x belongs to the x in this set. We are trying to prove x belongs to CL XB intersection Y, right? Then we will get the one-way inclusion. So to prove this, we need, see, x is already in Y, right? Because x in the closure of B in Y. So x belongs to Y is obvious. So we have to prove this one only. Prove just this one. Okay. So to prove this, we have to take, let V or say U be a neighborhood of x in where? Tau or tau y. We are trying to prove x is in closure of x, means closure of B in the topology x tau. Then from where we should take the open set, means an open neighborhood?
In X.
Tau.
Yes, from tau, right? Right, and we have to prove that this U intersection B is actually non-empty. You have to prove this one, right? But U is a neighborhood of x in tau. Now consider the set U intersects Y. Then this belongs to tau Y, right? By definition. And this is a neighborhood of x as well. Now apply this definition. Since x belongs to closure of Y being B, for any open set V containing x, means this will be the open set containing x, we have V intersection B is non-empty. Therefore, U intersection Y intersection B is non-empty. That's mean U intersection B is non-empty, right? Because this one is contained in this one. And so we are done. Means x belongs to CL XB. Therefore, what we can say, C closure of Y, closure of B in Y is contained in closure of B in X intersection Y. Okay. Now let's go through the reverse direction. Take Y belongs to CLXB intersection Y to prove X belongs to CLYB. Then from where we should take the take an open neighborhood and check whether the intersection is non-empty or not. Yes. Take neighborhood of X in where? Tau or tau Y?
So tau Y.
Yes, tau Y. Okay. So U be a neighborhood of X in tau Y. Then U will be some V intersection Y, right? Where V belongs to tau. Now look at this V. Then V will be a neighborhood. Now X belongs to here, means X belongs to V. And by this definition, we have V intersection B is non-empty. Okay, we have taken, and this will imply that V intersection Y intersection B is non-empty. And this will tell you that X belongs to CLYB. Therefore, this set okay. Now the next problem, then Is separability hereditary property? Means if x comma tau is separable, then and if we say phi not equal to y subset of x, and if we consider y comma tau y, can we say y comma tau y is separable? Yes. Tell me whether it is separable always or not. If not, give me an example. Yes, and this example is given in your note 3, which are sent to you on subspace. Now tell me the example. So tell me that example or anything. Means if you want, you can tell. So whether this is separable implies this is separable or not. If not, then give me an example. Yes, anyone?
No, sir.
Yes, this is not true, right? So what will be the example?
So Moore plane.
Yes, Moore plane. Moore plane, there we took the subset as the real line, right? That this one, the horizontal, sorry, the x-axis, right? Which has the discrete topology, right? Okay. So now if we take, but if we restrict the set y as if we consider y is open, if we add an extra condition, y is open in x. In other words, if we take y belongs to tau, then what happens? Then this y comma tau y is also separable. Okay. Now tell me whether x-axis in Moore plane is open in with respect to the topology. Is it open?
Yes, sir.
X-axis is open. What is the Moore plane? Oh, this is open. Oh. Moore plane is this one, right? Where y greater than equal to 0, right? And what are the open sets? Whenever y is strictly greater than 0, and if we take an element x comma y, this will be the neighborhood, right? But if we take an element from here, then it will be this kind of neighborhoods including that point. Right? Okay. Leave it. Look at the example. Oh, why I removed this one? Okay. Take x to be x comma y such that y equal to 0 Okay, this one means the x-axis union of 0, 1. Okay, now define a topology tau on X by empty set X and any set A where A is any set, a subset of X which contains or contains 0, 1, this point. Then this space will form, this will be a topology and this will be separable. Okay, but if we consider the set, this one itself, if you consider the set B, or if we take this as Y, then Y comma tau Y, we will have discrete topology. Okay, and in that case it is not separable. Okay, now let's come to this problem. So suppose now that your space Y is open. So take phi not equal to Y subset of X and Y subset of, sorry, Y belongs to tau. Then we will prove that this Y is, means then this Y comma tau Y, this topology, this subspace topology is always separable. Not always, always is not, it will not be a good word for here. Is separable whenever X comma tau is separable. Okay, so what will be the, okay, so let B be the countable basis, or let's say closure of X in B is X where B is a countable set. Then now take the set B1 as B intersection Y. So can you say that this closure of Y in B1 is Y? So how do you show? How do you prove? Means you have to prove that this closure of B1 with respect to the topology in Y is Y itself. Means this B1 is dense in tau Y or Y with respect to the subspace topology. So how do you prove?
Sir, we take any open set in tau y and then let's say V, then V intersection closure y B1 not equal to phi.
Yes, so then B intersection closure of B1 not equal to phi, then?
So sir, this is dense for every set, their intersection is non-empty. So this is dense and B1
Yes.
is countable.
Yes, yes. So okay, let's give some precise statement here. Okay. Actually, we have to prove this one. Now take an element Y from Y. Okay. Y from Y and U, a neighborhood of Y in Y comma tau Y. Okay, so you have to prove that this U intersection B1 is non-empty actually. Okay, so let's finish it here. So this is non-empty. Now, this, how do you write this U? So U equal to V intersection Y, where V is in tau. Now, Y belongs to V, here V belongs to tau. Okay, Y belongs to V implies V intersection B is non-empty. Right?
Yes, sir.
Yes. So can we then further say that V intersection B intersection Y is non-empty? Yes.
Yes, sir, because y is also
Yes. Y is because B is contained in Y, right? This is just a set theory. Don't go far beyond that. Actually, just use that much whatever you need. We just need a set theoretic argument here. To say from here to here, we just need set theory. Okay, and from here, what you can say? What is V intersection Y? This is U. Now U intersection B. Okay. So this can be again further say V intersection Y intersection B intersection Y, right? And this is B1 intersection U, because this one is U and this one is B1. So this is non-empty, and therefore we are done. Means closure of B1 is Y. Tell me if it is not clear. We'll explain it again. Okay. Tell me if it is not clear. Yes. Piyush, is it clear?
Yes, sir.
Yes. Okay. Then I hope it's clear to everyone. If not, then please tell me. Okay. So then let's move to the next problem. So it is given. Now see, in theorem, sir left one like theorem 12, and there are 3 portions are there. One of them is the inclusion map is continuous, and the second one is if f is continuous, if this f is continuous if and only if f from x comma tau to fx comma sigma, this means the subspace topology sigma of fx is continuous, and this is the third statement. So I think if I prove the third one, you will be easily you can solve the first two. Now tell me if some of you solve this one also. Now tell me how do we proceed? Like suppose this is continuous, then we have to prove that this is continuous. So how do you start? Yes, how do you start? Let U belongs to sigma B, right? You have to prove that F inverse U is open in X, or to say F inverse of U belongs to tau. This one you have to prove. So now U belongs to sigma B. What does it mean? U equal to subspace topology. Yes. B intersection B, exactly. So U can be written as B intersection B, where V belongs to this sigma, right? The topology in Y, right? So now look at what is your F inverse U. This is same as F inverse of V intersection B, right? Now I am giving you one argument. We will use this argument for this one and even for next theorem also, for next result also. This is just a set theoretical argument. Suppose you have a function f from x to y. Okay, and suppose a or say b subset of y, or say not let's cover in here itself. So suppose this b is contained in y is also contains fx. Then we can say that f inverse of b intersection b is equal to f inverse of b for all b subset of y. Okay, so can you quickly prove this one? This B, they said B contains the entire image set. Then, if you take any subset of Y and if you take the intersection, then this will be precisely the F inverse B. One Y is obvious, right? This F inverse of B intersection V contained in F inverse of U. This is obvious. Now for the reverse one. If we take W belongs to F inverse of V, this implies FW belongs to V. Now, but FW belongs to V, but FW belongs to Fx, right? And Fx contained in B. Therefore, FW belongs to V intersection B. So, W belongs to F inverse of V intersection B. So, what we have finally is that is F inverse of V intersection B is equal to F inverse of B. We will use this argument only. Okay. So now from here our B contains Fx and V belongs to sigma and V is subset of Y. Then from here, what can you say from here? This is
F inverse V.
This is F inverse of V. Now V belongs to tau. Okay. Now V belongs to tau and F is continuous. We assume that F from x comma tau to y comma sigma is continuous. Sorry. This is not in tau. This is in sigma. Okay. It's in sigma. This one. Now V belongs to sigma and if F from x tau to y sigma is continuous. So what can you say about this set? This is open.
Belongs to tau.
Yes. Open in x or open in x comma tau, or you can simply say this is belongs to tau. Okay, and therefore our F inverse U is in tau. So we have proved that whenever U is an open set here, U is open in here. Therefore, F from here to here is continuous, right? This is the restriction now. This is not restriction. We have taken a subset of the image set or subset of the codomain. Okay. Now let's move to the reverse one, to this one. So to prove reverse one, from where we should take the open set first? We will take an open set from. Okay. Tell me, shall I leave this one? Can you prove it?
Yes, sir.
Actually, I want to discuss something from quotient topology also. And there is one more important result called fasting lemma. This will be useful everywhere. Okay, so let me leave this one and just I'll discuss two problems and then go to the quotient topology. Okay, I think this is very easy. You can solve the reverse one. It's very easy. Okay, so can you see this one? See, if UI, this is an open cover, non-empty family, non-empty open sets. Basically, it's an open cover of X equal to union of I belongs to I and UI. Okay, and if F from X to Y such that each F is continuous in UI, but if F is equal to UI, from UI to OY is continuous, then this will imply F is continuous. Okay. So for this, what you do, you first take an open set from here, means an element from sigma y comma sigma. You first take an element v belongs to sigma. Okay. Now we look at f inverse v. Of course, this f inverse v subset of x. We can say it's that much. This f inverse v subset of x. So we can write this f inverse of v as this is equal to f inverse of v intersection of union of ui's. Okay, this is same as union of f inverse of v intersection ui. Then you will easily see that this is nothing but f restricted to ui, this inverse of ui. Okay, so this is an exercise. This is I leave an exercise for you. So from here to here, exercise. It's very easy, just application of set theory. And since each of f ui's are continuous, we can say that this is open in x, and therefore f inverse v is open in x. That's it. Okay. So is it clear? Just I leave here this exercise that f inverse v intersection ui will be f inverse of, sorry, if this is not ui, it is f inverse of v. Okay, so look at this one, you can easily solve. So next, this result. This is very important. Okay, very important in topology. So what is the statement? That x tau and y sigma, two topological spaces, and you have two closed sets, A and B, closed sets. Look at the last previous theorem or previous exercise. Here each ui was open set. Okay, but here these two A and B are closed sets, and such that x is equal to A union B. Okay, fine. Now you have a function A from, sorry, you have not from x, this is from, suppose you have two functions, one is f from a comma tau a to y comma sigma, and g from b comma tau b to y comma sigma. Okay, and both are continuous. These are continuous. Now we consider another function h from x comma tau to y comma sigma by h of x is equal to fx, when x belongs to a, and gx when x belongs to b. So can you please tell me, can you quickly tell me what further condition needed here so that h become an well-defined function? So tell me, is it well-defined?
Sir, x belonging to A intersection
Yes,
B.
this is, we do
F
not
is
know
equal-
what happens if x is an element of the intersection. Then further with fx equal to gx for all x belongs to A intersection B. That is why we have started two functions f and g, and here under the hypothesis that fx equal to gx for all x belongs to A intersection B. Okay. Then we say that if these conditions happens, then if we define a function, okay, let me state the question again, give the statement again. See, we have two closed sets A and B such that x is the union of A and B. We have two functions, one is f, one is from A to y, another one is g to y. both are continuous with respect to their respective subspace topology. And these two functions have the property that they are same in the intersection. Then, if we define a function h from x to y, which is if hx equal to fx for x belongs to a, and it is gx for x belongs to b, then h is continuous. H is continuous. So this is the statement of lemma. Proof is not that much difficult, but the statement is very important. So if we look at pictorially, suppose suppose you have this one. Suppose up to here this is set is A, and suppose from here to this side this is B. A and this is B. Suppose you have a function here. This is our f up to here, and suppose from here to here this is our g. Then we define the function h, which is a combination of these two. Okay, and then we will say that this function h is continuous. Okay, so how do we proceed? Since we are given A and B are closed sets, it will be better. It will be the question. The solution will be easier if we start with a closed subset of Y. So let C be a closed subset, closed set in Y comma sigma. Then can you quickly tell me what will be H inverse of C? Look at the definition here. So now forget about the closed set. Tell me, if we have this function, and if you take any subset C, subset of Y, then what will be H inverse of C? This is F inverse of C union G inverse of C, right?
Yes, sir.
Right? Others?
Yes, sir.
Yes, it is fine, right?
Yes, sir.
Then we can write H inverse C as F inverse of C union G inverse of C. Now C is closed in Y tau, and now come to here. F from A comma tau to Y comma sigma is continuous. So what can we say about F inverse C? F inverse C is closed in here, right? Closed in tau or closed in A comma tau or closed in A with respect to the subspace topology. Similarly, G inverse of C is closed in B comma tau B. Right. So F is continuous implies F inverse C is closed in A comma tau, right? So what is the properties of closed set in a subspace topology? This implies F inverse C is equal to
Sir,
what?
for some closed set intersection X.
Yeah, this is B, say B, not let's take it as S intersection A, right? Where S is
Closed in X.
closed in X. Now, it is given that A is closed in A and B are closed subsets of X, means closed with respect to the tau. Now S is closed in X, A is closed in X. What can we say? Their intersection, finite intersection is
Closed in X.
Closed in X. So F inverse C is closed in X. Similarly, G inverse C is closed in X, and therefore their union H inverse C. So H inverse C union finite union of closed sets F inverse C union G inverse C is closed in X, and hence H is continuous. Okay. Now this lemma. Okay. Tell me if the proof is clear. If there is any problem in the proof, tell me. I'll repeat the proof. Or actually, this result is very important in the course of topology. You can say if there are 10 pillars in a building, and if topology is the building, then this is one of them. And this lemma is called. Let me use another. This one. This is called Pasting lemma. Okay. Here it is written as a theorem, but it's we call its standard name. That's Pasting lemma. Okay. Yes. So is it clear? Actually, by this result,
Yes,
we construct some continuous functions. We also tell that if we are given some functions, if we can say that functions are continuous in piecewise, sorry, it's not exact piecewise, but if you can prove that the function is continuous over, if you can break the space X in finite union of closed sets, and if you can say that the function in each set they are continuous, and if they satisfy this condition, this intersection condition, then you can easily tell that this function is continuous.
Sir?
Okay. Yes?
Sir, if A and B are open, then this lemma is also hold?
Yeah, that's what we did here, right? Here the collection was arbitrary.
Oh,
go back and
yes.
see, right? Okay. So is there any problem? Yes. Quotient topology. Now let's come to quotient topology. Okay. This is recall first. Now tell me what is a quotient map? So suppose you have spaces X and Y. Okay, like just write it X and Y as topological spaces. Okay, so the topologies are understood. Y, let this be topological spaces. And suppose you have a, so what is a quotient map actually? So which condition you need to say that a map is a quotient map? Suppose you have a function say Q or from X to Y. Okay, so when do you say that this map is a quotient map? The first property is it is
Subjective.
it's surjective. And then the most important condition for quotient map, what it is? Yes.
A subset is open in Y if and only if Q inverse of the subset is
Open in X.
open in X.
Yes, exactly. So a subset, U subset of Y is open, or open of course in Y if and only if Q inverse of U is open in X, right? It was the definition of quotient map. Now there are several classifications that if a map, if we have a Q from X to Y is surjective, which is either open or closed, then it is a quotient map. But then Q is a quotient map.
तो इसको ऐसे भी सर बोल सकते हैं ना कि कॉन्टिन्यूअस सर्जेक्टिव मैप इज कॉल्ड क्वोशिएंट मैप.
Continuous सर्जेक्टिव मैप.
यस सर.
तो कंटिन्यूअस सर्जेक्टिव मैप उसको वो होना चाहिए ना. कंटिन्यूअस और सर्जेक्टिव होंगे तो हो जाएगा क्वेश्चन. नहीं होते ना. Okay, let me give you one quick example. कंटिन्यूअस ही होगा, सर्जेक्टिव भी होगा, लेकिन क्वेश्चन नहीं होगा. ठीक है. So take this one. Okay, what is this? This is x-axis, this is y-axis. Okay, and consider this line. What is this? Is the hyperbola xy equal to 1, I guess, right? Y equal to 1 by x. Okay, and including when x greater than 0 and including the point 0, 0. Okay, including the point 0, 0. Now consider a function q from, so this is our x. Okay, now consider a function this on this. So let's say this is our z set. Okay, now consider q from z to x, which is the projection. So that q of x comma y equal to x on. Okay, then can we say that it's a quotient map? So first of all, this is continuous, right? कौन बोल रहा था कि क्वेश्चन मैप वो नहीं होते, कंटिन्यूअस सर्जेक्टिव मैप क्वेश्चन नहीं होते. So this is सर्जेक्टिव, right?
सर मैं सिर्फ ये कह रहा था कि जैसे इसमें क्वोशिएंट मैप की डेफिनेशन गिवन है कि अगर कोई भी सबसेट ऑफ y मतलब ओपन लेंगे तो k इनवर्स u जो है ओपन होगा. तो कंटिन्यूटी जब होती है तो फिर होता है कंडीशन.
इतना सीरियसली मत लो, मैं दाता कहा ऐसे बोला ना. एग्जांपल
वो कोई बात नहीं सर. तो मैं कह रहा था कि मतलब कि अगर हम कोई ओपन सेट इन y लेते हैं तो सपोज q को f बोल लो ना सर, तो f इनवर्स u जो ओपन इन x, तो ये कंटिन्यूटी में एक प्रॉपर्टी होल्ड होती है, इफ एंड ओनली इफ.
कंटिन्यूटी में सर्जेक्टिव में प्रॉपर्टी होल्ड होता है.
नहीं सर, सब्जेक्टिव छोड़ दीजिए, अभी सिर्फ ले लेते हैं q कोई एक फंक्शन है.
हाँ,
तो हम बोलते थे कि अगर मान लो इसको कंटीन्यूअस फंक्शन ले लें तो ये प्रॉपर्टी ऑलवेज होल्ड होती है. और साथ में सब्जेक्टिव भी ले लें अगर,
हाँ सब्जेक्टिव भी ले लेते तो हो जाएगा.
यानी कि कंटीन्यूअस अनटू मैप जो है वो बोल देंगे ऐसे.
नहीं, ऐसा नहीं होते. इफ द कंटीन्यूअस और सब्जेक्टिव मैप क्वेश्चन मैप नहीं होते. ठीक है, मैं अभी तुमको दिखा रहा हूँ. ये देखो, ये जो एग्जांपल है ना, इसको देखो. ये तो मैप सब्जेक्टिव है ना, है कि नहीं?
सेट ऑफ इंटीजर्स है.
नहीं, सेट ऑफ इंटीजर नहीं.
तो क्या है
ये मैप क्यू है, z है मेरा दिस सेट. ओके, let me write precisely. Your z is x comma 1 by x such that x greater than equal to 0. Sorry, x quickly greater than 0 and union this set 0, 0. Okay, as a subset of R2. Okay, now to take this map q from z to, say it is R, which maps you this, the first projection means qxy is equal to x. Now this map is continuous, right? So this is just restriction of projection map, right? So this is continuous and this is surjective as well. One minute. We are taking r greater than equal to 0. Okay. Okay. इसको थोड़ा पूरा और कर देते पूरा कर देते इसको। इसको ना पूरा कर देते हैं, this one and this one. We are taking z to be x comma y, leave this set x comma y such that xy is equal to 1. This set union 0 0. Actually this curve, this one and this one, the hyperbola. Now we take the projection. Now we take q from z to r as a projection. This is the pio. The first projection means q of x comma y is equal to x. अभी देखो ये मैप कंटिन्यूअस है, yes?
No, sir.
Why it's not continuous?
Because sir, x tending to 0.
Yes, extending to 0.
Qxy goes to minus infinity and plus infinity.
Qxy is going to minus plus infinity. What is Qxy?
Sir, Qxy equal to x.
Yes, Qx equal to x. Now x tending to 0. We are taking first projection, right? This is not y. This is not y coordinate. Whenever we are moving to 0, our x coordinate should also move towards 0, right? And so this is x. Now, okay, tell me one more thing. You know the first projection map pi 1? Defined by pi 1 x comma y equal to x. Is it continuous?
Yes, sir. Qxy equal to x is continuous by sequential characterization.
Yes, this Qxy, this map is continuous, right?
Yes, sir.
Yes, so this map is continuous always. So if you have not learned already, then sir will teach you this one. This is called first projection. So anyway, so this map for the moment, this map is continuous, right? This map is also surjective. Yes. Yes.
Yes, sir.
Yes. This map is also surjective.
Yes,
now, but this map is not quotient map. Why? See, look at this point. Look at this point. So what will be a neighborhood of this point in Z? This, if we take Z 0 0, this singleton set is open in Z, right? Right? This is open in Z, right? Yes. अरे ये देखो ना, Z is a subset of R2, R cross R, right? So what are the open sets containing 0? So if you consider, because 0 0 can be written as, say suppose this is 0 0 equal to written as this set is, say suppose it is of radius r, means this circle of radius r intersect S1 intersection Z. This is open in R2. Therefore, what is the intersection? Only singleton set, singleton 0 0. Therefore, this set is open in Z, right? Yes. Yes, no. Is it clear that this singleton set is open in Z?
Yes, sir.
Yes or no? Yes, yes. Is it clear? The singleton set is open in Z? Now, what is Q of this singleton set? Image is zero singleton set. But zero singleton set open in R? R with usual topology?
No, sir.
This is not open, right? Therefore, what we can say, it is not an open map. Right? Now, let's see whether it is a quotient space or quotient map. Now, look at this set itself. Okay, what is the inverse image of this set? Now, say your U is this one, 0, sorry, U is the point 0 singleton set in R. Okay, by definition, this U is open in R. Means if we assume that Q is a quotient map, open in R, if and only if Q inverse of U is open in R, open in Z, right? This is the definition. But what is your Q inverse U? Q inverse of 0? What it is? It is only this set. There is no other point except this set. Right? Now you see this one is open, but 0 is not open. So we cannot say that it's a quotient map. Right? Is it clear?
Yes, sir.
Yes, sir.
Okay, so if it is clear, then fine. If it is not clear, please tell me. I will explain again. No problem, because this is the very important thing, the quotient map and quotient space. Means to understanding of quotient spaces. And these quotient spaces will be useful in topology courses or the courses related to topology like algebraic topology, differential topology. So and there you have to deal with this quotient space only. And I think everyone who know the topology space, they should definitely know this quotient topology. It's very important. So tell me if it is not clear. If it is clear, then fine. We shall move to the next problem. But even I will give the definition of quotient space also. It's the quotient map. Okay, so let me assume it's clear. Okay, so can you tell me, sir, whether sir taught you the saturated set, saturated open, or saturated closed set, or saturated sets? No, right? Okay. Now let's move to this problem. This is also the same kind of problem. So, okay. So before that, I want to recall the definition of quotient space. Let X be a topological space. So, what is a decomposition of X? Just a partition, right? And let X star, or say you had D, so let me write it as X star, a partition Okay, means this you can write X as union of this say B, where B belongs to X star. This is simply a partition. Now define. Then what we do to define a quotient space? We take a map, say F from X to X star. How? F of X is equal to
B such that X belongs to B.
yes, Fx equal to V such that X belongs to V, right? This is the class containing V. So see, this one is a partition. This one is a partition of the set X, right? So what are the elements? These are equivalence classes. So actually, given a partition, you can actually define an equivalence class. So can we say that an X? So let us take X tilde or X bar with the equivalence class containing X. Okay. Can say it define X tilde, and basically what you say, we take this V as denote this X tilde. Okay, the equivalence class containing X, right? Then this F is surjective, and we define a topology tau, say tau dash in X star as U subset of X star or is open, or in other words, U belongs to tau dash if and only if, or this is if is fine, or this case is F inverse of U is open in X, right? So by this way we define actually the quotient maps, sorry, quotient spaces. Okay, this is for your information. Okay, so in next day we will see problems from few more problems from quotient spaces, and for today we have one last problem that showing some map is a quotient map which is neither open map nor closed map. So shall I solve this one or leave it for you, this problem? Here we are taking the subset Z as previous, but here we are taking this subset, this one. Okay, look at the image. Where this is, suppose we have this is X, this is Y axis. We are considering the subset this one, this including, oh sorry, this one is consisting either X greater than equal to 0 or Y equal to 0. Means we are taking this one including this one, where X greater than equal to 0. Okay. Okay, so should I solve this one or leave it for you? So if you want, I have to solve. If you want me to solve this one, I will solve. Otherwise, I will leave it for you. Actually, okay, tell me quickly.
अभी लीव कर दो, उसके बाद नहीं समझ में आएगा तो पूछ लेंगे.
हाँ ठीक है. दिस इज ये अच्छा है.
एंड सर प्लीज अपलोड फाइल सर.
हाँ
और सर पिछली वाली सर फाइल आपने अपलोड करी थी.
हाँ, उसमें देखो ना जो क्लास मटेरियल्स है, मैं दिखा देता हूँ तुमको.
सर कहाँ पे?
ये देखो.
Yes, class materials.
इसमें.
ओके.
एक्चुअली इसमें सर डालते हैं ना बहुत सारे फाइल्स, जो फाइल्स है. इसको ये देखो, इसमें बहुत सारे फाइल्स हो गया ना, तो अगर सर भी कुछ डाल रहा है इसमें तो तुम भूल जाओगे कि मतलब इसमें बहुत सारे फाइल्स हो जाएगा, तो इसीलिए मैं इसमें डाला.
ओके ओके सर, वही मुझे दिखी नहीं थी।
इसमें देखे ना, और उसमें मैं आई लीव वन प्रॉब्लम दैट if we have a basis, means if a sub collection is the basis, then they are union, means how to form topology from a basis, वो सबको सॉल्व करना है, ठीक है। if you cannot solve it, you will not understand how the topologies are coming from a basis. And actually today I also thought to discuss about those quotient spaces, means examples, but so okay, can you give me 5 minutes so that I can present some more interesting question spaces? So sir, yes
सर, एक बार जो बेस ऑफ टोपोलॉजी डेफिनेशन है उसको एक बार से क्लियर कर दीजिए। जो बेस ऑफ टोपोलॉजी की डेफिनेशन ये थी कि मतलब every open set in tau can be written as a union of family of बीटा, एक ये डेफिनेशन हो गई।
हाँ,
और सर एक जैसे आपने वो लिखी थी अभी कि मतलब बीटा कवर्स x1 एंड सेकंड की अगर बीटा b1 एंड b2 के इंटरसेक्शन में बिलोंग कर रहा है देन देयर इज b3। तो सर मैं कह रहा हूँ कि अगर कोई बेस है मतलब टोपोलॉजी की तो मतलब ये दोनों प्रॉपर्टी सेटिस्फाई होंगी, और अगर दोनों प्रॉपर्टी सेटिस्फाई होते हैं तो क्या वो बेस होगा? तो इफ एंड ओनली
दोनों प्रॉपर्टी सेटिस्फाई हो गया तो वो बेस होगा। मतलब देखो एक्चुअली ये बेस होने के लिए ना, तो मैं बता रहा हूँ तुमको, नंबर 1 2 प्रॉपर्टीज था जो मैंने बताया था कि फॉर इसका for x means this x was union of b, right? B belongs to this script b, and second condition tha for x comma y belongs to for two elements b1 and b2, if we take x in the from the intersection, this will then there exists another open set b3 such that this x belongs to b3 subset of b1 intersection b2, right? ये था जो मैंने बताया था।
यस सर।
और उसके बाद तुम एक और बोल रहे हो, मतलब हाँ वो भी डिफिनेशन है कि एवरी ओपन सेट कैन बी रिटन एज finite union or arbitrary union of elements of B, right? एवरी ओपन सेट में तो x भी एक ओपन सेट हो गया, तो मतलब ये फर्स्ट कंडीशन सेटिस्फाई कर गया, ठीक है। नाउ फॉर द सेकंड कंडीशन, एक्चुअली आई एम ट्राइंग टू प्रूव दैट दीस टू कंडीशंस आर इक्विवेलेंट। Okay, now for second condition, suppose you have two sets b1 and b2, okay, and x belongs to b1 intersection b2। अभी देखो ये जो बेस सेट है ना, ये बेस सेट b is actually collection of tau, right? Her open set of b means her element of b are also open in x, right?
यस सर।
तो फिर ये तो हो ही गया ना, क्योंकि b1 इंटरसेक्शन b2 अगर तुम लोगे इसमें से तो ये भी एक ओपन सेट है, राइट? एंड बोलो कि एवरी ओपन सेट कैन बी रिटन एज यूनियन, तो फिर क्या हो गया, b1 इंटरसेक्शन b2 भी ऐसे हो गया ना, यूनियन ऑफ से सम j बिलोंग्स टू सम इंडेक्स सेट लैम्डा से bj, ऐसा हो गया ना। तब क्या हो गया, तुम इसमें से एक एलिमेंट लो तो एक कहां से आ जाएगा, x belongs to union of here ना, j belongs to lambda so bj, मतलब क्या है सर, there is some j not belongs to lambda such that x belongs to this bj not। अब क्या हो गया, तो x belongs to bj not subset of b1 intersection b2। मतलब अगर तुम ये सेट लोगे तो ये हो गया अगर ये एक टोपोलॉजी का बेसिस है तो फिर ये दिस टू कंडीशन सेटिस्फाई कर रहा है, ये आया ना। लेकिन अरे इसको ऊपर कैसे करें? लेकिन अब देखो, अभी मैं जब डिफाइन किया था तो मैं क्या किया था कि मैं कोई भी एक सेट लिया था X और उसमें एक कलेक्शन ऐसा लिया था कि X विथ कलेक्शन से सम B where B has the property that each element of B has this property, and then and then I defined a topology which is called topology generated by this basis. Okay, तो आप देखो ये जो टू है ना कि ये एक गिवन टोपोलॉजी से, हाँ कौन बोल रहा था, तो ये समझ में आ रहा है जो मैं बोल रहा हूँ?
यस सर, यस सर।
हाँ, तो अब देखो, हाँ, how to give you counter examples. हाँ, हाँ, अभी देखो ये R कंसिडर कर लो, ठीक है। R में यूजुअल टोपोलॉजी, ठीक है। R में यूजुअल टोपोलॉजी का बेसिस क्या है? दिस काइंड ऑफ फॉर्म्स।
यस सर।
A comma B belongs to R. Now take this kind of sets. Now take another set, say this one as this kind of set. ठीक है, जो सेट मैंने लिया ये भी तो वो सेटिस्फाई करते हैं कि यूनियन ऑफ सी से B belongs to C, B is equal to R and any to and for any to B1 and B2 with X belongs to the intersection. So क्या होगा? There exists some B3. X belongs to B3 subset of B1 intersection B2. अब देखो तुम्हारे पास एक टोपोलॉजी है R with यूजुअल टोपोलॉजी, ठीक है, एंड एक सेट है कलेक्शन ऑफ सबसेट्स which satisfies the condition of basis, ठीक है। But if we generate a topology with respect to this basis, this will not be the same topology as R. This will be the topology RL, right? The Sorgenfree line, right? ये क्लियर है? मेरा कहने का मतलब ये है कि अगर तुम एक सेट में एक बेसिस डिफाइन करो, वो बेसिस डिफाइन करने के बाद वो बेसिस एक टोपोलॉजी देता है, उसको हम बेसिस टोपोलॉजी जनरेटेड बाय दैट बेसिस बोलते हैं, ठीक है। और
यस सर।
सपोज उनको हम टाउ बी बोल दिया, लेकिन ये और ऑन द अदर हैंड दिस टाउ में एक और भी तो टोपोलॉजी डिफाइन कर सकते हैं टाउ पहले से ही। ये ऐसे बोल सकते हैं कि ये टाउ एंड टाउ बी मे नॉट बी सेम, ओके, समझ में आया? Actually, in second way, we define basis for a given topology. यहाँ पे टोपोलॉजी गिवन है, तुम्हें बेसिस ढूंढना है, तो अब इसको अप्लाई करो। अगर तुम्हारे पास कोई टोपोलॉजी नहीं है, अगर ये कलेक्शन दिया है, तब तुम इसको यूज करके एक टोपोलॉजी डिफाइन कर सकते हो।
Yes,
Okay.
understand.
That's why these two are different. But still, in both the cases, both the collection satisfies the properties of basis. Okay, but they can be basis of two different topologies defined on the same set. Okay. Yes. So anything else? Yes.
Sir, is it possible to get your WhatsApp number?
I have shared it in the last class.
Okay, sir. Thank you.
Look at there. Actually, generally it will be better to send me something through MS Team only. You can send me through MS Team chat.
Okay, sir.
I'm active there always. Yeah. So actually, Carl. Okay, let me stop recording.